Hello everyone, my name is Shanice Abraham and this is my lab report for Lab 1, Constant Velocity. The purpose of this lab was to investigate the motion of an object moving at constant velocity and comparing the data collected to a computational model. The main principle for this experiment is Newton's second law, the momentum principle. It states that the change in momentum equals the net force times the time interval. F net equals mass times acceleration. If the net force is zero, the momentum and velocity would stay constant. In this lab, I observed the marker moving at a constant velocity after the initial kick, and my model confirmed this observation. The system in this experiment was the marker, and the surroundings included a foot that applied the initial kick and the surface the marker rolled on. Once the kick stopped, there was no additional forces that were acting in the x direction, so the marker continued at a constant velocity. The materials we used were a marker, meter stick, a computer with tracker app, and WebVPython. I placed the marker at the 0 increment and gave it a kick to the right and recorded its motion. From this movement, we observed that the marker moved at a relative constant velocity. Next, I imported the video into Tracker and aligned the axis so the position X matched the marker's motion and tracked the marker's position from the time it first moved. If I had flipped the axis, the data would look negative, but the physics would actually remain the same since the slope of the line would still be constant. It would just give a different interpretation of where and when the object started to roll. Tracker then generated a table of X position versus time. Then I took those values and put them into an Excel spreadsheet. Next, I built a computational model using the starter code provided. I set the initial position and velocity from the values I received from the tracker table. Then I used the last time input from the tracker table for the parameter of how long the while loop should last. That way the total time matches the experience and what actually happened. Then I changed fnet to equals 0, 0, 0 since there were no additional forces acting on the marker after the initial kick. Using Newton's second law, I created code that would update the velocity and position step by step. It would take the initial velocity of the marker and add it with the net force divided by the mass times the change in time. Then the position would be updated by adding the marker's initial position with the new velocity times time. After the code finished running, it produced a table of position and time values. I then took those values and added them to an Excel spreadsheet. After that, I graphed the tracker's data values and the coded values and saw that they produced straight lines with almost identical slopes. This means that the position increased linearly with time. Since the slope equals velocity, it shows that the marker moved at a constant velocity. It also aligns with our initial observations when we watched the marker moved. This shows that the model and the experiment are in agreement. There were some small differences between the model and the video that could have made some differences between the data that we saw. For an example, there could have been friction between the marker and the surface or small tracking errors in the tracker app. These errors were minor because the results still showed that the marker was in constant velocity during that time. What this shows that even though the net force is 0, it does not mean that no forces exist. It just means that the forces are balanced out so that velocity stayed constant. If there was a net force, we would see curves in our position versus time graphs, which would indicate changes in velocity and a non-zero net force. In conclusion, both my observation and my computational model showed that the marker moved at a constant velocity after the initial push. This confirmed that when the net force of an object is 0, an object's velocity remains constant, just as Newton's second law predicts. Thank you for watching my Lab 1 report.